Here we have a single force acting on an object of mass 3 kg. The force acts on the object such that the position of the object as a function of time is given by x equal to 3.2t minus 2.2t squared plus 1.6t cubed, where x is in meters and t is in seconds. We are required to find the work done on the object by the force from time t equal to 0 to t equal to 6.5 seconds. Recall that from the previous question we defined the work done by a variable force as WD is equal to the integral of the force, which is a function of x with respect to x, from the lower limit to the upper limit, say x0 and x1. In this case, we don't have the force directly, we just have the position as a function of time, and we have the mass. But one thing we can find is the force from the acceleration. We know that the force acting on an object is given by the mass of the object times the acceleration. We also know that acceleration is the second derivative of position. So if we take the derivative of our position twice, we will get an expression or a function for acceleration. So let's do that. Dx dt from what we have here will give us 3.2. The exponent of t in the first term is 1, so it goes away, and here we have 2.2 times 2 t, 2 minus 1, and then I have plus 1.6 times 3 t. This will be 3 minus 1. Therefore, dx dt is equal to 3.2 minus 4.4t plus, this will give me 4.8t squared. Now we're going to take the derivative of this expression again. So we have a, which is given by d squared x, the t squared, second derivative. When you find the derivative of a constant, it goes away. So derivative of 3.2 is 0, derivative of negative 4.4t will give me 4.4, and the last one will, the 2 will come down, multiply 4.8, and that will give me 9.6, and the power will drop by 1, so it will be t. So now we have an expression for acceleration. Now we can go back and substitute that into this first expression, f. So we have f equal to mass times acceleration. Therefore, f is equal to, the mass is given by 3 kg, so we have 3, and then we have minus 4.4 plus 9.6t, and this is in Newton. One thing we would notice about this first expression is that it's a function of time and not a function of x. The question is, can we use same work done expression if the variable is time? The answer is yes, and we just have to do some manipulations. And here we go. If we want to transform this expression, work done, given by x naught, x1, f of x dx, to an expression in t where f is a function of time, then we have to find dx, a function of time, dt. And we're going to see that when we do the substitution. So work done will be t equal to 0 to t equal to 6.5. The force we have is 3 into minus 4.4 plus 9.6t. Now, if you recollect from, okay, we have it here, we have that the x over the t is given by this expression. So we're going to look for an expression for dx here. So it implies from our first derivative that dx is simply 3.2 minus 4.4t plus 4.8t squared dt. So instead of having dx here, we're going to have the equivalence of dx, which is 3.2 minus 4.4t plus 4.8t squared dt. And this is the expression we need to integrate to get the work done. An easy way to compute this integration is to use U substitution. We can see that negative 4.4 plus 9.6t is the derivative of 3.2 minus 4.4t plus 4.8t squared. So if I substitute u for 3.2 minus 4.4t plus 4.8t squared, I can transform this integral to a simpler integral where the variable is u. And this is obvious with this next step I will take. If we take the derivative of u with respect to t, we would have negative 4.4 plus 9.6t. And you can see this is what I was referring to. This term here, the derivative of this term gives you this term. When that happens, you can use U substitution. So I can solve for, actually, I can simplify by finding du. Du will be negative 4.4 plus 9.6t times dt. If you look back at the work done integral, we have 3 here. Integral from t equal to 0 to t equal to 6.5. I can write this second expression first. So I have 3.2 minus 4.4t, I'm just rearranging, plus 4.8t squared, multiplied by the first expression here, minus 4.4 plus 9.6t dt. And now we can see that this whole expression is simply du. Therefore, work done is now the simpler integral. We're still noting that t is 0 to t equal to 6.5. Remember, this first expression we called u here. So here we're gonna have u replace all this, and du will replace all this. I know I'm supposed to transform my integrals to u values. The values I'm substituting, my upper limit and my lower limit and upper limit to u, but I wouldn't do that. I will just do this integration and put back the value of u, or the expression for u in terms of t. So work done is now equal to 3. This integral is just u squared over 2. And by substituting back, we have 3 over 2, 3.2. I'm putting back what u is originally, 4.4t plus 4.8t squared, and all squared because u is squared. And now we can substitute t equal to 0 for lower limit, t equal to 6.5. Okay, so we have our work done here. We'll go with 6.5 first. We have 3 over 2 bracket 3.2 minus 4.4, 6.5 here for t, plus 4.8, 6.5 squared for t again, and then square because we have a square here, minus the lower limit substitution. We have 3 over 2 here, bracket put 0, all 4.4 times 0 is 0, 4.8 times 0 squared is 0, so we're left with just 3.2, again squared. So I'm just going to use my calculator to find what that sums up to. Okay, I'm going to do the inside brackets without skipping much steps. So I'll have 3.2 minus 4.4, 6.5 plus 4.8 times 6.5 squared, all squared, times 3 divided by 2. So this first substitution gives me 47206.14 minus, I'll do the next one, times 3 divided by 2, and this only gives me 15.36. So I'm going to take the difference now. So I have 47206.14 minus 15.36. And that gives me the work done on the object by that variable force as 47,190 0.78 joules. So in conclusion, if your force is in time, you can still find the work done. So we know that work done again is force when is a function of position times integral of the force as a function of position with respect to the position. This is equivalent to the integral of force as a function of time times the derivative of position with respect to time dx. And that's just what we had. I mean the t. This should be t. So this works. This expression works when your force is in terms of position and when you find your force in terms of time. Thanks for watching. I hope this was a beneficial video.